Okay, I think we can start. I will share my screen. Okay, so thank you everybody for joining this webinar. My name is Ahmed Shoaib. I am the JMAG engineer at PowerSys, and today I'll be presenting, or I will be introducing right now the topic of this webinar, which is next generation of EV motor design using JMAG Designer. This webinar is pre-recorded from Mr. Nebayan Cebulski. He is available for answering questions at the end of the session, but we will be playing the recording during this webinar. He works at IAV GmbH in Germany. He works at the System Development E-Traction department at the IAV. And in this work, he will be showing modern approaches to design or modern approaches and design to face the most demanding FEA simulation tasks. I will now start the video. We will be having a question and answer session at the end of this webinar, at the end of this presentation. So if you have any questions, please type them into the chat, and we will try to answer them by the end of this session. Okay, let me go to the video quickly. Let me double check some. Oh, sorry, I need to. Oh, sorry. Not sharing, and then I need to share again. Share screen. Share sound. Screen to share. I hope that's start from the beginning.
Hello and good afternoon to my presentation with the title Next Generation EV Motor Design using JMAG Designer. In the next 45 minutes, I'm proud to introduce you to some of our design tasks and methodologies that we use in everyday's work to design electric motors for hybrid and electric vehicles for automotive customers. My name is Bernd Cebulski and I'm the responsible team manager for electric motor design. At first, let me say some words to my company. IAV is an engineering service supplier that is developing components and systems for the automotive industry. On the right lower corner, you are seeing some of our customers, which are mainly car manufacturers and tier 1 suppliers. Besides the automotive industry, we are also working on other areas like aerospace industry or wind power, energy stuff, also robotics and other things. Regarding electric motors, we are doing any kind of stuff, starting from very small 1 watt stepper motors used for air conditioning system and other stuff, up to 500 kW big electric drives for sports cars and heavy-duty trucks. One of the examples of our developments I can show you today is the electric motor family that has been developed for IAV's battery electric vehicle platform. The idea behind this is to establish kind of a platform where the motor ranges from small motors from A-type cars up to big trucks or sports cars using similar iron sheets and as much as possible same parts. And this can be utilized and applied to certain customized developments. If it comes to e-mobility, there are a lot of specific requirements that somehow deviate from industrial applications. Starting from a niche production, e-mobility has grown to a very big industry, which has many facets of different developments and different requirements. So it's hard to address everything in just one slide. So we have frequencies up to 1 to 3 kilohertz, very fast running electric motors with more than 20,000 RPM. We have different voltage ranges, currents starting from 50 amps for very small motors up to more than 800 amps for big motors. And also the life cycle endurance somehow deviates. For the car, it's of course much lower than for heavy duty trucks, where the requirements are quite similar to the wind power industry. And we have to assure that especially for high voltages, we meet the high life cycle expectancy of our customers. So the general requirements really depend on the application and the different needs, different customer markets. So the result of this is, of course, different e-machines that you see on the internet or some presentations which use various design approaches that somehow give you the question, how in the world did the designer come up with that idea? The answer is different requirements. If we talk about electric machines, there are many topics that are somehow interconnected to each other. The slide here focuses only a few of them. There's much more if it comes to electric motor design, and only a few of them can be addressed by finite element calculation. So for instance, of course we are facing the efficiency, especially the driving cycle efficiency is one of the main points which everybody knows about. But besides that, you also have to care about the failure behavior, the functional safety concept, or high voltage safety. This is putting somehow very big compromises on the design, which lead to the motors you see on the market. When you come from university, you always think about the best motors, the most expensive materials, and highest performance that can be achieved. But in practice, this is not always possible. Due to the different requirements, you always have to find compromises. So a real optimization is hard to achieve here. The basic recipe of an electric motor is quite easy to understand. On this slide I have it simplified to a very easy formula. So it's basically copper, iron and rare earth if we are talking about permanent magnet machines. And of course for insulation you need some resin and plastic parts. So the main machine design task is simplified to find a compromise or a mixture of all these parts and materials to give you the best performance and the best working machine. The function that an electric motor has to achieve, besides its transformation from electrical to mechanical power, it has to conduct electric currents, which is mainly the part of the copper. It has to produce and conduct magnetic fields, which is mainly part of the iron and somehow also the magnets. It has to insulate the electric voltages, otherwise the motor of course is running in short circuit. And there are mechanical tasks like the relative movement of the rotor against the stator, which needs bearings and other parts to get the required torque out of the motor. So all that comes to a cost of heat and noise that you of course want to minimize. There are plenty of different types of electric motors you see in the market. And if we talk about electric vehicles, there's one dominating technology, which is the permanent magnet synchronous machine. Why is that? If you look at the right picture, you see the different machines and their strengths and weaknesses. You see the permanent magnet machine is the red area where most of the properties are really on a good level. One of the disadvantages is really the high cost of the magnets, and there are some safety issues. Whenever you turn a permanent magnet machine, there is an induced voltage that you have to care about. Besides that, all the other machines have different strengths and weaknesses, and they have also their application in the electric vehicle industry. Especially the current excited synchronous motor is very popular in Germany due to no use of rare earth materials and also good safety properties. There are also low-cost solutions where some of our customers are focusing on the induction motor. Although you don't see it so much on the internet, it's still existing in development phase. A lot of things are going on behind hidden doors, some developments that you don't see on some internet publications. Reluctance type is somehow difficult due to its high noise and bad NVH behavior, but also to the higher costs of the inverter, because you need some higher apparent power, some higher current for the inverter, which puts the price on a bad edge. So the main focus also on this presentation is the permanent magnet synchronous machine, especially the type with the interior magnets. If we talk about JMAG, we are talking about a low frequency Maxwell solver, how it's called. So it's meant to be used for the magnetic field distribution in ferromagnetic parts. Besides that, it can be used to calculate torque in forces, losses in iron parts, in conductive parts. You can use it also for calculate electrical fields, transient events, for instance, failure events like the two-phase or three-phase short circuit, but also the recovery from the short circuit, which is also difficult. Besides that, there are also system integration things like simulation together with circuit simulators, which are used to simulate the control behavior of the inverter or other connected parts. And also there are simulations that are outside of the electric motor. You can also simulate magnetic sensors like the resolver, for instance, or the coupled problems between the electric machine and the resolver. Due to the stray field, there might be some disturbances on the sensors, which can also be simulated using JMAG. And then there is the big field of manufacturing effects, which I will also address in this presentation. Due to different manufacturing, there's a lot of influence on the magnetic and electrical properties of the different part of the electric motor, which needs to be taken into consideration here. The same applies for the permanent magnets that have different errors or non-idealities that needs to be covered if you want to reach a high level of accuracy. So the result of that is that the finite element calculation, of course, does not solve every problem, like Professor Miller has already stated out in another presentation, but it can help to predict a lot of things that are related to physics, and it can be quite accurate and really help to get rid of some difficult to conduct tests, for instance. So if we talk about simulation accuracy, what does that mean? So why do we need that? The simulation is conducted for different reasons. So as I already stated out, you have to use, or you want to have a high accuracy to get rid of very expensive tests of the electric machine, but you also want to have already results if the machine is not really existing, so you want to predict the performance. And then there is also a scientific side. You want to understand the electric machine, you want to see some effects like the bearing currents, for instance, which are hard to be measured but can be simulated. So how can we achieve a high accuracy? Of course, we need a very fast computer, which makes it possible to use a high mesh density. We use better convergence nowadays. It means you can also face problems in 2D and 3D, which weren't possible in years before. So you can model eddy current problems very efficiently, which is also quite new, especially in 3D. And you have very modern GUIs, which make it possible that there are some engineers that use JMAG are maybe not so experienced. So they are not specialists in electrical engineering, but they can still use JMAG to investigate those certain problems. And one of the strengths of JMAG is the very good modeling of the winding geometry and the winding features. Especially with the latest version, there have been many improvements to model 3D geometries of hairpin windings, but also round wire windings, which make it quite easy to make a real winding in several minutes, I would say. Before that, you would have to model this with very expensive CAD systems and import the geometry into JMAG, which incorporates a lot of trouble. Still, there are existing a lot of problems for achieving high accuracy. One of the topics is the material modeling, where we really have problems since the theory is just not good enough to describe everything in mathematical equations. You need a lot of measurements, and there is still some work needed to make iron losses, for instance, more accurate. There are many problems which can only be simulated in 3D. The problem is that this is very time consuming. The system approach is somehow limited, also due to calculation time, due to some things that are hard to be simulated, and other things like anisotropic behavior of magnets, steel sheets are issues. And as I already stated, the manufacturing influence. The problem is not the simulation in this case. The problem is that you just don't know what are the non-idealities. So you have to measure the iron sheet after manufacturing, which is not possible so easily. So it's somehow guessing about the manufacturing influence. The goal now is really to reach something like 1% accuracy for the losses, which is very hard to achieve. To really get to this goal, you need many improvements and a lot of experienced things. Although I do not want to stress the efficiency map so much in this presentation, I have to mention it, since this is, of course, one of the main tasks of the electric motor designer. For this kind of stuff, we have automated scripts at IAV that we use, where we can generate automatically cycle efficiency, very comprehensive maps, not only efficiency, also torque ripple, radial forces, some losses, the aggregation of losses, and other things. So as you see here on the picture, there are certain areas where the efficiency is quite high, which is in the middle of the area for an IPM machine, and there are certain areas where the efficiency is low. The problem now is that the driving cycle that is used to estimate the CO2 losses of an electric vehicle are normally located in an area where the efficiency is not so good. So this is somehow a compromise for the design to find a good machine which has an overall good efficiency but also faces the cycle efficiency. And for this low torque region, there are a lot of influences from minor losses things or minor losses parts that you have to look at. For instance, there's a big area of AC losses. What does AC losses mean? AC losses is a phenomenon that is basically occurring from alternating magnetic fields that are cross-sectioning the conductive parts. So whenever you have a winding with a big cross-section that sees an alternating magnetic field, either for its own or also the neighbored conductors or from some rotating magnets, there will be some induced eddy currents in the conductive parts, and this is what we call AC losses. The effect will be more severe if the frequency is high and the magnetic field is high, of course. It can be looked as a superposition of the base current of the conductor with some magnetic field coming from the outside. You have to deviate between the skin effect, which is purely based on the geometry alone and its own field, and the so-called proximity effect, which is basically an influence from the other conductors and the magnetic field that comes from the outside. So the eddy currents and the so-called current displacement increase with conductor size, with frequency, and also with the electrical conductivity. So to use a worse electric material is good for AC losses. Of course, that's bad for DC losses, so you have to find compromise here. And if we look at electric vehicles now, we see a lot of so-called hairpin windings in the market, which is basically a foam coil winding based on copper bars, which is of course very susceptible to eddy current losses, and we have a lot of problems with that. So you see an example of a real machine. On the left side, you see the non-equal current density on the bars. You also see that the worst effect is on the top bar. This is due to the effect that the rotating magnets have the biggest influence, of course, on the top bar, and the lower bar in the slot ground does not have so much influence here. So it also matters where the location of the copper bar in the slot is. In reality, these locations are mixed due to the interconnection of the different slots. You normally have more than one slot per phase. And so you can optimize this phenomenon somehow by placing the bar in different positions of the slot. On the right side, you see the effect of the different AC losses. On the upper portion of the picture, you see a efficiency map without any AC losses, and the lower part is with AC losses. you see that mainly the high-speed region is affected. So this is mainly a problem for sports cars, for very small motors running with high RPM, or some solutions where the car has to run 200 kilometers per hour, for instance, which is the normal case in Germany, by the way. The problem is that you have to use the full AC loss model for all map calculations, which is very time-consuming calculation, and for optimization this is difficult. One of the things that also influences the AC losses is the conductor shape. If you look at the lower pictures, there are possibilities to use small narrow bars or use wide bars. These shapes of the bars have of course a different influence to the AC losses, so you have to optimize this for lowest AC losses. But of course it also depends on the machine operational points that you want to optimize. Depending where your driving cycle lies, you have to reflect this by the different shape of the bar here. So you cannot just optimize by one point, you always have to look at the driving cycle here. You see the different results here for different conductor width to height ratios here. There is a big influence for additional copper losses. Another topic is the material. As I already stated, the higher the conductivity of the material is, the more severe is the AC losses effect. This is due to the inner physics of the material. So one might think, why do not make the conductors of aluminum, which has a lower conductivity than copper? Problem is here, you want to have high conductivity due to the lower DC losses, or at least low frequency losses. So why not mix that? You can use aluminum bars on the top portion of the bar and use of the slot, and use copper in the lower portion of the slot. So here on the upper part you see different shapes and formations of bars that you can do, starting from solid copper to some O-formed aluminum to some mixture of these materials. And you see that depending on the frequency there are very different AC losses. If you do the same calculation for the cycle, like it's done here on an example machine on the lower portion, you see that the difference regarding WLTP losses is quite small. It's only 0.3%. So the thing is that aluminum, of course, is much cheaper than copper and also more lightweight. So this is an area of optimization that you can take if it's about cost and weight of the machine. And if you have the money to produce that kind of mixed materials, of course, you have to solve things like the interconnection between the materials and so on. But electrically, this can be a quite promising approach. So the same here investigated about costs and different arrangements. In the left portion, you see 4 copper bars, in the middle 2 copper and 2 aluminum bars. On the right side, 4 aluminum bars, and yet you see here that there is a big effect in cost and mass. So we don't see these machines now, but this is something we might look at in the future to have lower cost and better efficiency in high-speed region especially. Of course, as I said, it depends on the machine type and on the requirements of the machine if we really need to pull that. Especially machines with very high frequency are worth looking at this topic. So another thing is the shape of the cross-section of the copper bars. One of the ideas that you might have is to use different shapes for the different conductors. So you can use a big cross-section on the lower bars and a small wide cross-section on the top bars. This could also be used as a kind of optimization. So it means the individual conductor dimension can really help to reduce the AC copper losses. But as always, it depends on the operational point. So it's not possible to optimize for the entire operating range. You have to focus on the operational points where you really want to optimize this thing. Besides that, there are other solutions on the market or in physics that you probably all know. One is to use Litz wire. Litz wire has the disadvantage that the copper fill factor is quite low due to the air between the thin wirings. But the advantage is really that the AC effect is compensated due to the different positions of the different wires here. Of course, the FEA calculation of such a Litz wire is quite complicated, since you need something like 25 million elements in the example shown here to really get a picture of how the current distribution looks like. And this is even a simplified model with a certain Litz wire type that is not the best one. There are different Litz wire types and topologies which are very difficult to simulate in 3D, but it's possible, as you see. Another approach that is mainly used for bigger machines like wind power industry is the so-called ripple bar or continuous transposed conductor. You see an example here. The idea is basically the same. The difference is that you use much bigger geometry, some rectangular cross-section, and transpose the different subconductors and arrange that to an entire big conductor. This can also be calculated with JMAG. Of course, you need 3D models to investigate about this. And we have done comparisons to different shapes of this stuff. And this is promising, as I said, for big machines. It's nothing to use for smaller EVs, since it's also quite costly. And then we have proven a third approach, which is based on 3D printed copper bars. Maybe it's not so easy to see it in the picture, but these bars are made from printed copper. So we have every degree of freedom to make whatever shape you need. On the right lower portion of the picture, you see the FEA calculation of such a stuff, of such an arrangement. All the other bars are made of massive copper, and I used just one bar with that idea here, because it's just a time-consuming calculation, which needed several days in this case. And also convergence is an issue. And the problem here is really you need very high frequency to pull advantage out of this design. And of course, it's still expensive due to the additive manufacturing here. But it's still something worth looking at if you are trying to design a racing sports car or some, I don't know, aerospace industry motor where you can spend some more money on the motor just to get the performance. AC losses are not only existing on stator winding, it's also existing on other conductive parts in the system. For instance, the copper bars inside of the inverter or the interconnection bars between the different winding parts. So as you see on the left higher animation here, the current is not flowing in the entire cross-section anymore, it's flowing only in the edges. And so you could imagine that this is quite bad for the heating of this kind of copper bar. The current stress on those bars can be very high. And if you are thinking about simulating the heating of those bars, you have to look at AC losses or current distribution regarding high frequency as well. That's the same also for conductive housings that are around magnetic fields. For instance, in DC-DC converters, if you are producing some reactor coils and you have stray fields where there are some conductive aluminum parts, you also have to look at the stray field. All this is possible in 3D with JMAG now. Besides the magnetic field, there's also an electrical field. This is quite unusual to talk about, since I don't think many of you have already done some electrical field simulations. But since we have also electrical stress in the winding on the insulation system, we also need to know how strong the electric field in the different part of the winding is. Really to design the winding and to make sure the insulation will survive the life cycle. The problem is that the inverter we use for electric vehicles are switching faster and faster. We are now in the step of changing the silicon IGBT to a silicon carbide MOSFET with a much higher switching speed, and this is incorporating additional stress on the windings due to the overshoot of the switching. It gives really high voltage on the winding, and there occurs a phenomenon which is called corona discharge or partial discharge, which will destroy an insulation system in hours. So if you really have that problem in the winding, you have to do something against it. Since we also have very high power electric motors, which are running on 800 up to 900 volts, the corona voltage on the first winding can reach values up to 1300 to 1500 volts. And this is already an area where you have partial discharge. So the idea is here to get electric field calculation to be able to predict problematic areas and do something in the design for the electric machine to make it survive longer against this current discharge, or maybe get rid of it at all. On this slide you see some example. The left picture shows a stator slot, the ground of this stator slot, and you see the electric field distribution here. The black line is a cross section of the entire stator, and you see the different voltage levels here. This might seem as a quite simple problem where you don't need to establish FEA. You can do also analytical calculation. But if you look at the next, there are much more difficult problems in reality. We have now oil-cooled machine where there is some oil used for direct cooling of the winding heads. And with it oil drop on conductive parts, you have a local increase of the electrical field strength, which can lead to partial discharge in a certain area. Even very small oil drops can make a partial discharge to occur. Reason is that the permittivity of the oil drop is somehow different to the insulation system. Insulation system is something between 4 and 5. The oil drop, as you see here, has a permittivity of 2, and then there is air with a permittivity of 1, and all that leads to an increase of the local electrical field strength, which can reach very high values and lead to partial discharge. Another area where this is useful is the end winding. Especially with hairpins, the different phases are very close to each other at the end winding portion. If you don't insulate them with specific methods, you're having very high field strength, reaching an area where you have corona discharge, and will get a destroyed winding. So the idea is to put some insulation paper, something like Kapton or PDFE or anything like this between the different phases to make sure there is no partial discharge, or if there is partial discharge, the material have to survive that for a certain life cycle. So you might think that this is a quite easy simulation, but I can tell you it's not. Not only because it's 3D, the biggest problem is here the meshing refinement does not have to be taken in the material. You need the meshing refinement in the air, since everything related to electrical field strength is looking at the air region and not in the materials, because in the material the electric field strength is constant. So this is you need a very specific meshing model here to make this simulation converge. Another approach or use of 3D simulation is the end winding inductance. This is a kind of a mysterious value that most people are estimating using analytic formulas, like it's done in other FEA programs. And I can tell you from measurements as well as from 3D simulation, all the analytic models that are existing in literature are wrong. It depends, of course, on the electric motor you are looking at. So as you see on the comparison here on the left part, it can be quite close, like here with a pole per number of 8, but it can be something like a factor of 2 and more inaccurate with other combinations. So covering every type of machine, every pole per number, every different winding scheme is not possible by analytical formula. So for a specific machine, you have to do 3D calculations to make sure you get the right winding inductance. Otherwise, you're not able to predict the right power for the high-speed region and have also some other effects. In this particular case, of course, also simulation is quite complicated, especially if you have to consider the AC losses, like it's done here. This is a really long-term simulation, but luckily you have to do this only on certain operation points, and you can transport this to a correction factor, which you might apply to your analytic formula. Here's another picture of the same phenomenon, where we try to use the AC current distribution although the field in the end winding region is quite low, there's still a very high effect on AC current distribution. So if you're interested in that, you also need to establish some comprehensive simulation. Another area of application is the mechanical stress. I'm striving this only shortly because our focus is electromagnetic design and not mechanical design here. Nevertheless, you have to make sure that the rotor will survive the high speeds. So whenever you do optimization of the rotor, you need to take care about the rotor stability. For that purpose, we use also JMAG in 2D. And you see here some optimization of the air chamber next to the magnets. You need very fine meshing in the region where the stress is high. And you see already that there could be some design changes applied to lower the stress in that region. So this is also very nice in JMAG, although for more comprehensive simulations, we need 3D programs, other programs to make sure that the machine is really strong enough. Yeah, another big topic is the manufacturing influence. There are many topics related to the manufacturing influence. One of the biggest problems is here at the design stage of an electric motor, you don't have really an idea about how the machine will be manufactured. So you really need to establish manufacturing flow at a very early stage and to try to cover this already in simulation. On the other hand, different manufacturers produce different problems. It's not only a question of the machine type and the stamping method, it's also a matter of tolerances and maybe wear out of the stamping and other things. And also there might be some production improvements that you cannot be foresee in your design, which you also need to consider. So to focus really on manufacturing at a very early stage really assures that you can provide a stable design that will not change if the machine is really manufactured. One of the areas is the so-called degradation of soft magnetic material. Whenever you put mechanical stress or heat on a soft magnetic part, its magnetic properties will change. So regardless if you do laser cutting or punching of the steel sheet, you always get changes in the magnetic properties. This is especially true on the edges of the part, of course. You can simulate this kind of stuff with JMAG. There is a simulation model to really incorporate the stress-induced change of the magnetization curve and the losses. The problem is really you have to know the properties. So at first you have to measure your iron sheets, and depending on the manufacturing method, like laser cutting or water jet cutting and punching, the influence to the magnetization curve, especially in the lower region, is quite big. Of course, in saturation region, there's not much change, but in between it, there's a very big influence. So especially if you have very thin teeth, like in the example here, or in induction motors where the rotor teeth are normally very heavily saturated, you have to look at this kind of effect. And if you don't, there are big deviations in performance, and most people then are surprised why there is such a big deviation because they did not consider this kind of effect. Another problem is the magnetization curve itself. So the BH data that you get normally from your manufacturer or that you get from JMAG database is somehow limited to 1.6 or 1.8 Tesla. But in real machines for electric vehicles, the magnetic induction can be higher than that. And the question is always what happens above. So the theory claims that the saturation of silicon iron really occurs early, and this is faced by kind of extrapolation in JMAG. But if you use different extrapolation methods that are available in JMAG, you get very much different results. So when you have a design where the machine is heavily saturated, you want to check what the different extrapolation areas give you for a result. Currently, I cannot give you a good result. What is the best approach to face that issue? At least you have to think about this. Best way is, of course, measurement, but it's not so easy to measure things with higher than 1.8 Tesla. Things got severe if you don't use only silicon iron. If you use, for instance, cobalt iron, which has much higher saturation flux density, the things got even severe. So this is something you need to consider. Otherwise, the simulation results will be very inaccurate. When you measure the magnetization curve, or you get measured data from your manufacturer, you might get some ripple in the BH curve, as it's seen here on the red part. So what are you going to do with that? You could do some interpolation, which I have done here in the left curve, which is a double logarithmic description. You see the quite complicated formula here. There are tools that can do that kind of stuff quite fast. The problem is it's still not reality. It's just interpolation. And if you look at the right curve, you might think that this ripple and the interpolation is just fine. But regarding the permeability, there are big changes due to this ripple. So depending on the interpolation that you apply on this curve, you get different results in simulation. The second problem is the monotonic shape in an area lower than 100 amps per meter, where you normally have to do some smoothening of the curve for better convergence of JMAG. It's not really necessary. Most problems do also converge with the black curve, but to help JMAG, especially in big problems for convergence, it's better to use kind of a flattening of the curve. But this is also introducing an error, since this is not physical reality, of course. So please look at the magnetization curves and make sure you're using the right data. This is very important for accurate results. Another area of FEA calculation is the eddy currents inside of conducting magnets. The material that we use for high-performance motor is mostly neodymium iron boron and somehow samarium cobalt, both of them being electrically conductive. So whenever you have a changing field in conductive media, you get eddy currents. The problem with the magnets is that the magnets heat up due to their eddy currents, and since normally they are not so good thermally coupled to the environment, they can overheat quite easily and can be demagnetized. So you have to take care about this eddy current, that it's not getting too high, and need a quite accurate calculation. What we normally do is we do a 3D calculation and derive some correction factors from the 3D model that we use in 2D calculation. And you also might consider segmentation of the magnets, like here is axially segmented. You can also radially segment it to reduce the eddy current. And this is something you might also cover by FEA calculations, or you need to cover even. On the other hand, there are several inaccuracies in the magnet itself. So the ideal case that you normally apply to simulation is the left part. However, the reality is not like this. In reality, you get magnets with a lot of errors in the magnetization, like shown here. The inhomogeneous stuff can be caused by different material problems. It can be caused by wrong magnetization. There's something which is called end effect, means that the sides of the magnets are not the same as the middle, and you can have something like the north-south pole effect, where the north pole is stronger than the south pole. It means that the area in the middle is shifted somehow. Some of the things really can be modeled with finite element programs, but not all of them. This is something that has been left out for the future, for improvement of JMAG, to really make it possible to simulate that kind of stuff easily. On the other hand, you also need to measure it, of course, to make sure you have the right model here. Right now, there's no easy solution in FEA, but there will be some solution in the future, I'm sure. Then there is something which we call packeting and welding effect. So for manufacturing, you might use welding for the stator packet, or you use some notches and some steel parts here to connect that together. This is, of course, a short circuit for the magnetic field and incorporates additional losses. So also another thing to be calculated if you want to reach the 1% losses accuracy goal. This can also be quite comprehensive depending on the machine topology, of course. The influence in this motor was negligible, but that depends on the machine geometry, of course. Then there are several actual end effects. Not only the end winding itself, but also the rotor part has some end effects. If you have a skewed rotor, there are some actual components of the magnetic flux that you need to consider, which might lower your air gap flux and lead to lower torque in the calculation. You see here two comparisons, one being the torque in 2D and one the torque in 3D, and you see quite big, I mean relatively big deviations between those two values. Also, if you look at the induced voltage, the back EMF, you see the deviations from the two different models. So this is also putting difference in the noise evaluation, as you might imagine. Then there is a big area of NVH calculation. There are several different approaches. You can do analytical simulations, you can do comprehensive FEA simulations in 2D, you can do 3D FEA. At the end, it's about forces. So the thing that influences NVH most is the radial forces. So you have a transient turning machine in 2D or 3D and calculate the radial forces. There will be some map which comes out here regarding in space and time. And with that calculated force mapping, you go into your mechanical simulation, trying to calculate the deformation of the materials and at the end the noise radiation. So at IAV we have a integrated tool chain where we use JMAG as an electromagnetic part and several other tools, also some IAV own tools to get calculated noise radiation. We are also able to validate this by a specific measurement chamber, a noise isolated measurement chamber with some microphone matrix. And yeah, this is quite comprehensive calculation, but yeah, as you know, the EV should be running very smooth. You don't have the combustion engine anymore, so you have to take care about the noise. Another topic is the current and field harmonics. When we do simulation, the current is normally sinusoidal. In reality, of course, it isn't. So there are many effects coming from this harmonic current and harmonic field, which is the following then. There are several sources of these harmonics, which could be a nonlinear back EMF. Saturation is one of them, but one of the biggest influences is the inverter itself and the control system, of course. We are feeding the machine with PWM. There are some non-idealities on the inverter, like the dead time and delay, and the control algorithm itself might introduce some harmonics here. Of course, to calculate these harmonics, there are different approaches. One of the approaches shown here, so you can use a circuit model together with a JMAG RT model to simulate the currents, or you can do a full co-simulation with MATLAB Simulink, for instance, to get the real control system. Depending on what you are using, the simulation time is quite different, of course. But at the end, you really get the real currents and fluxes, torques, noise, and so on from PWM influence. This is getting more and more important, and we are now in the stage that we are calculating every map with PWM influence, if we have the time and can do this, of course. There are a lot of additional losses and forces related to this effect, which needs to be considered if you want to have an accurate simulation. For the modulation methods of the motor control, there are several different algorithms. When you are a motor designer, you are normally not so much aware of those control stuff, but you have to if you want to simulate the losses in the right way. Some of the examples being space vector modulation, the discontinuous PWM. There are much more than just these two methods, but these are just the most utilized ones. And you could imagine with that kind of current shape, you really get a lot of noise and different effects in the machine. I've talked a lot about permanent magnet machine. Of course, there are other machine types on the market, which we also face in our projects, although the PSM is really the dominating technology right now. But we are doing simulation with induction motors, 2D and 3D. This is a small stepper motor used for a special application. There is different magnet arrangements here. There is the current excited permanent magnet machine. We have the axial flux machine, which is quite difficult to calculate since you need mostly 3D calculation. And of course, there are many actuators and more stuff that you need to do. So JMAG is capable of handling all these problems. It's only the automation is somehow different. So for a new topology, you always have to establish a new tool chain and to be fast enough. So calculation, especially in 3D, can be quite time consuming. So now I come to the conclusion of my presentation. The losses calculation has many different topics, even much more than I have presented today. Some of them are already everyday work and some of them are really difficult to address, and some of them are even impossible to address right now. But there are still a lot of things that we can improve for the future regarding simulation accuracy, regarding JMAG capabilities. I think machine design in 10 years from now will look much different than today. Second point is you need a detailed knowledge of the material and the manufacturing influence. This is a very important point. As I have stated out in my presentation, problem is you need difficult measurements, you need maybe partners, some university institutes which have experience in those kind of measurements. Right now there are some standards of this measurement procedure, but in my opinion they are not good enough. So magnetization stuff is really different in the teeth as in the yoke, and you might need different material models for the different parts of the machine, even if you use the same material. The control and PWM influence lowers the performance and needs to be modeled, of course, either using a correction factor or using a full co-simulation. JMAG really has strong capabilities to use that kind of stuff, and it's improving with every version. The finite element calculation can solve more problems than just losses, magnetic fields and torque. Especially if you don't focus only on electric machines. You might use sensors, magnetic sensors or other sensors that use magnetic principles. You can use JMAG even to conduct some experiments to understand phenomena in physics. So this is an endless story. The motor designer needs to know not only its electric machine, but also the surrounding system. Not only the inverter, but also the gear train puts some additional forces on the rotor side, which also can correlate with some magnetic effects. So it's more or less system things that we also have to face now. So it's not only the motor itself. Then we are more and more using 3D simulations for increased efficiency, but also for certain special effects or for better understanding of the machine or even for manufacturing things. The 3D problems are still time consuming and memory consuming, so it's really hard to do that in everyday's work, since normally not every customer is willing to spend the money for this. But to really improve your accuracy, there's no way to avoid this. Proximity and skin effect are issues that are really faced every day, I would say. Regarding the main winding, this is already a standard process. Regarding different things like the housing, eddy currents and other things, sensors might still need some improvements here. Yeah, then some points that I want to state out is the measurements are not physical reality. Whenever you compare your simulation to the measurements, you are comparing apples with pears. Since even the measurement is not reality, measurements has its own failure, has its own accuracy problems, the reality is never known. So when you do that, comparing simulations to measurements, always think about that the measurement accuracy is also limited, especially in the area of very high efficiency and very low torque. So to think about how to improve measurements and what kind of specific measurements you might take to get a better idea about specific losses is always a good idea. The machine designer should also know how the electric motor is measured. A thing that I already stated at the beginning is that the efficiency maps are not the truth about electric machine performance. So please don't look only on the electric efficiency map, which you see very often on internet presentations as somebody wants to sell you its electric motor. Efficiency map is just one point. It might be the most important one for the car designer, but it's sometimes not the most important for the electric motor designer. Functional safety issues, noise issues can be much more important and lower the efficiency at the end. So besides the magnetic stuff, there's also a lot of mechanical losses. So don't forget about all the mechanical losses that have also influence on efficiency. This is about bearing losses, but it's also about air dragging losses, which is a quite complicated area of research. We don't have round cylinders. There's a complicated geometry in the stator, and also the rotor surface might be shaped. So to really get a good picture about these air dragging or windage losses might be very important, especially if the machine has a very, very high rotational speed. With more than 20,000 RPM, the mechanical losses might be the dominating losses in that region. So to estimate this accurate is difficult, but it can be measured somehow. You can use models, 3D printed plastic parts to get a better picture of this kind of losses. So the end sentence here is the FEA simulation needs much more than just efficiency map. This is basically the idea of my presentation. So thank you for your listening, and I'm open for questions now.
Okay. I hope you can still hear me. Again, sorry. So now we will be taking questions. Please type them into the chat. I will be reading them out. Mr. Cebulski is available for answering questions. We are a bit tight on time, but we'll try to get 1 or 2 questions in. I'm not seeing, okay, let me check in the Q&A. I'm not seeing any questions right now. It was a very comprehensive presentation, to be honest.
Yeah, just in case you have some more questions after this presentation, please feel free to send me an email or use social media to contact me.
Yes. Okay. Then I will close the session for now. I will like to thank Mr. Cebulski again for his attendance or for this presentation. And as stated, please feel free to contact us if you have any additional questions later. Thank you and have a good day.
Yes, thank you from my side as well.
Okay, goodbye.
Goodbye.